Hello, my name is Alan Rose from Corrdesa, and I'm going to talk about software tools and workflows for corrosion prevention planning. Okay, so in a word or two, what's my background and that of Corrdesa's? We spend a lot of time helping our clients define, develop and deploy modern materials, and this process can take quite a while. And where we find ourselves working, we've done a lot of work in the sustainment area. We've worked with Department of Defence. We've seen corrosion issues, material degradation issues. We've even developed and deployed some equipment for fixing electroplated coatings. That's what you can see here. But the main thing is, having seen these examples, we can see that some of them should never really have occurred, and maybe better choices here to the left in design could have avoided these problems, and we just really should be in sustainment maintaining coatings, not trying to fix problems that should never have occurred. So using this experience, we've started at Corrdesa developing corrosion prediction modeling software tools, and we take into account what we've learned in testing. We can actually create virtual test chambers, you could say. We use the simulation tools for optimizing coating stack-ups, and we can take into account various operations such as different missions and environments. And all of these elements can really be managed in a commercial PLM such as Siemens Teamcenter. So we've created a bunch of these tools that can be managed in the Teamcenter, and I'll show you that later on. So why corrosion simulation? Well, it's all about safety, cost, compliance, and obviously performance and durability of your product. Safety issues, for instance, in the past there's been issues of corrosion starting off around fasteners and then ensuing fatigue and cracks and so on. And we have here an example of the fuselage that was ripped apart due to corrosion. In fact, the FAA have reported that 23% of failures are related back to corrosion. The cost is huge. Globally, corrosion costs a lot of money, 3.1% of the global domestic product. And many studies have shown that with various tools and better data, a lot of this can be eliminated in design, about a third of it, a third of the cost. So it's important to see what tools are out there that can be leveraged to reduce this cost. And it takes an awful long time to deploy these new coatings and materials. Even if they've been invented and you have the chemistry, you still have to go through the qualification, validation, and so on and so on. And that can take a long time, and with simulation, that can be sped up considerably. All those decisions you make early on in design, you live with, and contribute a lot to the sustainment cost. Even the military is still using B-52, which is like 7 decades old. Certainly on the military side, well, you could also say on the civilian side, readiness. If your plane or asset is in the shop, in the depot, being fixed, it's not making money for you, it's not ready as a warfighter. So working with folks such as the Air Force, they are continuously fixing problems in sustainment to which they think should never have occurred and could have been eliminated in design. So if we drill down a bit, I was talking about the costs. Even in the Department of Defence, the cost is $20 billion, and you can see how it breaks down into the Air Force and the Navy, Marine, Corps Aviation and so on. So that represents a fifth of the total maintenance budget just dedicated to fixing corrosion. So that consumes an awful lot of technical hours. So why are we facing this problem? The fact is, you can design your plane, you have your coating stack up, you have sacrificial coatings there that kind of kick in if there's any defects or scratches. But those coatings become consumed. Water does ingress. Things, your parts of the plane or the vehicle will move. So you really should have tools to look at what if scenarios. What happens if water ingresses here? I can try and avoid corrosion by sealing it, but most things degrade or break up. So you need to look at that. And you know, it's a difficult problem because it's not just a simple environment. You know, these assets like this, an airplane, for instance, can operate different altitudes, different geographical locations, experiencing different temperatures and humidities. The Lunar have monitors that can be affixed to the assets, and you can get more information about that. And then even inside and outside the asset and different areas of the asset have like kind of sub-environments, you could say. And then, you know, there's like singular environments like this where you literally have tons of salt water just being dumped on the assets. Okay, so where do we start? There's many mechanisms of corrosion. One particular one was galvanic corrosion. The Navy, US Navy, really had problems with this. It turned out that in teardown studies, it was shown that the FA-18, more than 80% of the structural fatigue issues were related back to galvanic corrosion events. So obviously that was very important. And you can see when you take the skin off these structures, the corrosion in there is really bad. And this really impacted the readiness of the FA-18 some years back. It got as low as 50%. Half of your fleet is not available to fight. So you look closely at the corrosion caused here, and you know, how do we fix that? Certainly around bushings, we'd have to remove the corrosion and then somehow bring that hole back to dimension. You know, if this is like for fasteners, you put that bushing in there, and you can cold fit it into there. So it's important what materials those bushings are made of, because you're going to start a new interaction there. There are a lot of fasteners, so you don't want to be doing this process for each and every fastener. So you need to make material choices, coating choices that can avoid this. Now FA-18 is a older platform, but even in the newer assets like the F-22 had an issue, and that single issue, corrosion issue, cost $228 million, and that was to do with a conductive gap filler. And we were asked or told by folks that we presented this technology to, you know, literally, I'll believe it if you can show that it would have avoided this $228 million problem. And indeed we could. We have done some studies with the materials of concern in the kind of geometry, and found, of course, that would have been flagged up early on, and you could have made some other choices to reduce that considerably. It's interaction between, you know, carbon fiber composites and the aluminum structure, and of course that conductive coating. That all can be analysed up front in design. Okay, let's talk a bit about computational corrosion analysis. So essentially, we need to take a step back. For instance, many folks would be familiar with the galvanic tables. So at high school, electrochemistry, you would have learned of the galvanic tables and how a larger potential difference would suggest a larger corrosion risk. So if we were to consider an aluminum structure and think, okay, let's use these stainless steel fasteners, and I was to look on a galvanic chart there, I would see that that potential difference is smaller than the potential difference between aluminum and titanium. So the suggestion is, oh yes, let's use stainless steel. That will cause less corrosion. But over here on a curve from experiments, you could see various couples put together, titanium and aluminum, and stainless steel and aluminum, several different kinds of stainless steels. And you can see on the vertical axis galvanic corrosion current, which is proportional to the galvanic corrosion rate. And you can see for the titanium aluminum, it's actually much smaller, despite what the table said. So essentially, a mill standard 889 used to use this potential galvanic series, and it was actually inaccurate for some cases like this. So mill standard 889 for galvanic corrosion has now actually been changed. It's a paradigm shift. We no longer use potential differences. You have to actually calculate the galvanic corrosion current, and for that you need polarization data. So there's a lot more data that are required, and you have to be careful how you go about acquiring that data. In the appendix, there's a protocol explaining how to do that, and it's applying mixed potential theory in order to assess what the corrosion rate might be between different materials. So with that in mind, now you can see with this test, with the titanium fasteners and the stainless steel fasteners, where the corrosion rate is higher around the stainless steel fasteners, and we can predict that as well. So the mill standard 889D came out, and what we can do now is there's a table in there with a number of materials, aluminums, different alloys and so on. So you can see these three materials that I've just introduced, and on this table you can see the intersections, and you can see that we have a corrosion rate class 2 for the aluminum 7050 and titanium, whereas it's even higher for the 7050 with the stainless steel, and you can see the legend over here on the right. So now that's more accurate, which is great, but the day that the standard was printed, it becomes out of date. What do we do with new materials? Well, there is a protocol, like I said, in the appendix that tells you how you go about measuring these. So you can go measure them, get the polarization data, and then you can cross the polarization curves, and you will find that corrosion rate between those two materials. So we captured this in our software. This is the Corrdesa software. You can go to corrosiongin.com. And one way of thinking about it, it's an electronic version of the mill standard, and you can see all the data. You just go straight to the substrates there, and you can click and see the pages and pages of data that we have, and also a lot of coatings. So but if you have access credentials, you can then use the corrosion analyzer. So what we do, we have different environments, 3.5% sodium chloride, kind of a maritime environment. There's also the mill standard 889D environment, which is artificial seawater. So we have all that mill standard data, and we can compare materials, material 1 against material 2, and you can see here how we're making the choices of that aluminum 7050 structure, and then considering what the a stainless steel fastener would do coupled up against that structure. So I have quite a lot of different stainless steels available. We click them, we have this substrate designation, coating and treatment. We can look at different treatments. It pulls the polarization curves, and there's your materials, the aluminum, which in this case is anodic, and then over here we have the stainless steel, which for this case is cathodic. But the guts here is down in these tables. We have the self-corrosion rates of the materials, but the kicker, of course, is when you couple them, and that corrosion rate is much, much higher. You can see it's in the red or pink zone, or number 5 there for the mill standard. We can copy that very quickly, and we have a new group of material 1, material 2. It self-populates, so now we can just swap out the stainless steel for the Ti-6-4. It's very quick. It's just a click, 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 and run the analysis. Pulls curves again, and this time the titanium Ti-6-4 is cathodic, and the corrosion rate is much, much less on the aluminum. Okay, so titanium is shown as a better choice, but maybe titanium is a little bit expensive for the asset. What other things could you do? Well, we could perhaps apply a coating. Let's do a zinc nickel coating on the fasteners. So it's no longer seeing the stainless steel, it just sees the zinc nickel. So we choose that as a coating. We have a dip salt coating here. Now you can see the aluminum is cathodic and the coating is anodic, so it's sacrificial. So the corrosion rate here, although it's it's low, it's the corrosion rate of the coating. You got to remember that. So it gives you an indication of that consumption rate of the coating. But the key thing, of course, is that the aluminum is experiencing no corrosion. Now the mill standard makes the assumption that the area ratio of anode to cathode is 1 to 1. But what we've done here, we have a facility where we can put in a different area ratio. So let's say the aluminum is 10 times the area of the fastener, which is quite likely if you've got small fasteners. And you can see that the corrosion rate here is considerably less. It's like 56 microns, whereas it was a couple of hundred before. So you can take into account the area ratio. You can't do that in the actual military standard. Okay, so what did we do there? We just very quickly did some trade studies. We had 4 material couples. We coupled aluminum with a stainless steel, aluminum with a Ti-6-4. Then we considered a coating, and then we looked at the difference of what would occur if we had an anode-cathode ratio that was non-unity, and we have the summary here. So now that capability, or I should say that the standard has been changed, it demands the polarization data, and there's a lot more we can do with that polarization data. So we have our electrochemical database, and what we did there was the curve crossing, essentially using mixed potential theory. The intersection of those polarization curves will give you that corrosion rate. Now what we can do, we've completely integrated our software, Corrosion Gin, in a commercial CAD package, in this case a Siemens NX software package. And I'll just give you an example of how that helps you, because it automates that calculation. Then if, for instance, you still have some issues and you want to get into the detail on what the impact of the design of that fixture system might be on that corrosion rate map, you can calculate that using a multi-physics solver such as CCM+. I'll show you a couple of examples there. But I'm often asked, should it be materials people doing simulation, or simulation people learning more about materials? And there is a kind of a grey zone there. And what we did do, we created some templates. So the materials and process people, with their expertise, their domain expertise of materials and corrosion, can use these simulation tools with this templated in this templated way, and I'll show you a couple of examples there. Okay, so let's consider this in another way. So when I've used Corrosion Gin, that's for materials engineers, you could think of that as a corrosion risk. Okay, these materials adjacent to each other, not a good idea. What can we do to mitigate that? Maybe change the material or coat it, as I showed in the example. And we can automate that process for a whole assembly that can have thousands and thousands of interfaces, and you can do that literally in minutes. Or you can consider, rather than once you've done the corrosion risk piece, you can then deep dive and maybe do a 3D model on those areas of particular concern, something that may be more stubborn and you can't work your way out of it with a coating. You might have to alter the design. So here we have the Corrosion Gin completely integrated into NX. So this is the NX CAD software. You can see here, if I click on that member there, you can see the material data. Now, with the NX Coatings module and the corrosion analysis indicator, you can do a corrosion risk analysis. Just like before, you can choose your environment, 3.5% sodium chloride or the mill standard. There's other environments that we've done for other clients as well, for personal devices and so on. So what we can do then, we choose one or all of these components, and it's found, the system has found all those interfaces. So let's calculate the corrosion risk, galvanic corrosion risk on all those interfaces. So it's just a click of a button. We have a color code there from red, yellow to green, and we can see here there's a higher corrosion rate on this particular material pair. So it shows you that the aluminum part of that pair is anodic and this titanium here is cathodic. So we can kind of look deeper into this. We can study that interference, and there are features within the CAD system, as you can see, it zooms in there so we can tumble, roll, and try and get a better idea of where that galvanic corrosion issue is between these particular materials. We can also click on that pair and we can get the report, and you'll recognize this is essentially the GIN report. So what the system has done is it's automatically found all those interfaces and it's run GIN for each one of those, so you can deep dive into any of those reports. So let's restore the visibility and try and find out, you know, what's going on here. Why have we got this kind of a sore thumb corrosion rate? The material there is Ti 3, and we find that for similar materials between these ribs and spars, we actually have Ti 6, so which has a much smaller corrosion rate on the aluminum. So essentially, I've seen this happen before, and I've used this as an example. The designer has accidentally picked the wrong titanium alloy, and this has been highlighted with this automatic analysis. So that can be easily fixed. Another thing, what does the purple mean here? That just means that in the NX materials database, we don't have that particular material, but you know, we're adding more materials to it all the time. Okay, so we've swapped that material back and there's no more issue there. Let's have a look at some other things. What we can do is, as before how I looked at coating a fastener, we can do that here. We can choose these clips, apply a zinc nickel coating there, as you can see, and now all the coatings are anodic because they're actually coated with the zinc nickel. So that way you've forced your aluminum to be cathodic. So there we go. All right then. So you know, that can be done. That was just an aerospace example. We also have, of course, done work in automotive, and you know, we can do the same thing with this chassis type example. There, it would quickly find all those material pairs that have a high galvanic corrosion risk. So that can be quickly done with the press of a button, and once you've found those risks, you can just order them from your high corrosion rate down to your low corrosion rate, and then start looking at those higher corrosion rate risks. So here we have the high corrosion rate risk, and it's this piece over here that was highlighted in yellow and red. It's actually aluminum 6013 versus the steel 1008. And we can find, if we just swap out that aluminum for a 2024, we can reduce the corrosion rate from 226 microns significantly down to about 30 microns a year. So that's very quick. You can just try different coatings and different materials while you're actually in design, sat inside that 3D CAD. What you could do, so what we have here, I've said the 6013 with that corrosion rate of 226, and then we swapped out the material there to reduce that corrosion rate on the aluminum significantly. But over here, the component in red, there's actually 4 pieces to that. When we do the NX analysis, it just looks at it pair by pair just to quickly try and find some risks and highlights. But if you want to look at the impact of several coatings, several different materials, and several components all kind of conjoined, then you really need to get into a 3D model. And that's what we've done. You know, we've seen that there's a problem here. Let's create a sub model there. So we took that CAD, put it into CCM Plus, and you can model the corrosion. There's several electrochemical modules within CCM Plus. We picked the secondary current density assumption module, and you can see the material assignments here and how the aluminum has a higher corrosion rate, which was what was shown in the NX indicator. But in 3D now we can see the corrosion rate map. Let's swap out that material, and you can see how we've zeroed out the corrosion on that aluminum by changing its material. Still some corrosion here between the two different steels. And maybe we can swap out one of those steels and reduce the corrosion even more. So we've gone from a maximum corrosion rate of 317 and more than half to that particular corrosion rate. And we can do it further by bringing it down to about 80 microns a year. Okay. All right then, so you need to be a bit of an expert to do that kind of a model. You have to create the geometry, you have to mesh it, bring in your materials. And we work with the Air Force to create a templated version. So very quickly we can build some 3D models that can be very informative when it comes to making decisions. You know, simulation is for decisions. So recognizing that aerospace components are made of many repeated components such as lap joints, butt joints, bushings, fasteners, doublers and so on, we created a library of parts, as you can see here. So the materials and process engineer can run this GUI that sits on top of CCM Plus. It's very easy to use. They just enter in the dimensions over here according to this lap joint that's bolted, for instance, and then over on the right side they just enter in the materials. And this can be done in a matter of minutes. I've seen this done in like as little as 8 minutes, setting up one of these models. It automatically creates that geometry and the fasteners and any kind of sealant in there. It automatically creates the computational mesh, and very quickly you can look at the impact of different design decisions. You know, should you have an insulator in there when you look at this aluminum and carbon fiber composite joint? Should we are we good with the 17.4 pH, or should we use titanium fasteners like we were talking about earlier? And you can very quickly look at those issues. So why is that useful? We actually use this on a real geometry on a C-17, the fuel access door. And what we did, when you look at it closely, you can think of the port and the aircraft skin being a butt joint, as I've highlighted here in Model 1. And you can think of the fasteners, it's repetitive. So we just think of a fastening lap joint. So what we have here is our surrogate models. You can see on the right hand side where I've just talked about the butt joint Model 1 and the fastened joint, the Model 2. So we put in the appropriate dimensions and the appropriate materials. It's very quick and you can see the results of the surrogate models over here on the right. On the left we actually built a full 3D model, albeit it's repetitive. We actually modeled the full 3D geometry, and in that it took us a few days actually to clean up that geometry, and well, now it may be just a matter of hours. We got a corrosion rate of 331, and then within minutes, using the surrogate approach, we got a corrosion rate of 321. So virtually the same, but we found that solution in much less time. So it recognizes that kind of geometry. You're not having to make assumptions about area ratio and so on. It's actually pulled in that representative geometry, and we've done it very quickly. So corrosion toolset and workflows. There's ways of deploying this. We've deployed it in Teamcenter. You can see here how we have run the Corrosion Gin in Teamcenter. We can pull the CCM Plus in Teamcenter. All managed, everything all in one place. Your electrochemical database, your results, all the simulation files and so on. So by managing it in that kind of environment, you don't lose the data, and you can just build on that knowledge base. That was a requirement from the Air Force. That's the PLM model of choice, and you can see here how it flows all the way through to the actual simulation within Teamcenter. It's very quick. It just takes a few minutes to solve for that lap joint example. Okay, so to conclude, it's I talk about different user personas. Okay, so we have materials and process engineers, we have simulation people, we have design people. All have want different results at different times to guide what they do, reducing corrosion. So it's like a toolbox. So corrosion chain is CAD agnostic. We can use that very quickly upfront in requirements. As we develop the model, we can constantly check that the materials being chosen across the enterprise, because it's not just one person that designs these complex systems. We can run the NX corrosion analysis indicator to be sure that everything, all the corrosion risks are minimized. And if we need to go into a deep dive, we can use a multi-physics model, the STAR CCM+. It can be managed within Teamcenter or not, depending on your organization. So, if you want these slides and you want to go through them, I'll give you an email address shortly. You can reach out to me. You're free to contact me with any questions. Here's my acknowledgements. We've done a lot of work with the Air Force Corrosion Prevention and Control Office. So I thank my colleagues from that office and of course from Siemens, our partners. Any questions, like I say, send them to me, Alan Rose, arose@corrdesa.com. There's more information on our website as well. Thank you.